Hello, everyone, again to the conference on AI and architecture. I'm so happy to introduce to our next speaker, Dr. Ricardo Vinuesa. He's an associate professor at the Department of Engineering Mechanics at KTH in Stockholm. He's also the vice director of the KTH Digitalisation platform and lead faculty at the KTH Climate Action Center. He studied mechanical engineering at the Polytechnic University of Valencia in Spain, and he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand, control, and predict complex wall-bounded turbulent flows, such as boundary layers developing around wings and urban environments. And Dr. Vinuesa has received, among others, an ERC Consolidator grant, the most prestigious research program in Europe, the TSFP Kasagi Award, the Göran Gustafsson Award for Young Researchers, the IIT Outstanding Young Alumnus Award, the SARES Young Research Award, and he leads several large Horizon Europe projects. And finally, he's also a member of the Young Academy of Science of Spain. So please, warm welcome, Ricardo. The floor is yours.
Thank you very much for the introduction. It's a real pleasure to be here. Today I'm going to be speaking about our work on artificial intelligence for sustainability. This is funded by the ERC, but also by Digital Futures. So I'm happy to be here in Digital Futures talking about some of our work on these topics. So let me start by introducing some success stories of machine learning and why this type of technology is having such a big success nowadays. Starting with image recognition, I mean, of course, being able to understand patterns in vehicles, in different types of vehicles and cats and dogs on the internet. Turns out that humans have a 5% level of error in this type of tasks. And now deep neural networks can do this much better, now with only 2% error. There's many other tasks where machine learning is outperforming human performance, predictive tests, data analytics, finance predictions. Maybe one early story was this game in 1997 where Garry Kasparov, the world champion of chess at the time, was playing against the IBM Deep Blue machine. And as you can see, he was not very satisfied with the result. It turns out that IBM was able to defeat Garry Kasparov. He was very upset and claiming all sorts of cheating by IBM and so on. That turns out that he was asking to get all the code from this system, and turns out that he was in a way, without knowing, starting the need for interpretable machine learning. No? I mean, there is the necessity to know what these algorithms are actually doing deep down. The reality is that chess is a relatively simple game for machines. Almost with brute force computing, it's possible to play chess very well. There is another game that became very popular after Google DeepMind, which is the game of Go. And Go is a significantly much more complex game. You can define the complexity of a game by taking the number of moves that you can make in a particular turn and raise that to the power of the number of turns that a particular game takes. So this m to the power of t. And you can see that Go is many, many orders of magnitude more complex than chess, no? In terms of the combinations that can happen within a particular game. So there is a real challenge where it was expected that only many decades ahead, machine learning was going to be able to tackle this game, because you cannot solve it with brute force computing. You need some sort of intuitive strategic thinking to be able to complete this task successfully. Maybe unsurprisingly, because we know already the outcome, and this is work by Google DeepMind from already 6-7 years ago, and what they showed was that it was possible to develop an algorithm based on the best games of human players of Go. This is the AlphaGo, the AlphaGo algorithm. And they confronted this algorithm with the best human player, which is this picture that you can see here, against Lee Sedol, and AlphaGo defeated him by 4-1. So it was really, again, a very, very surprising outcome, because it was one of the first times that in a very complex task, machine learning was developing quite prominent superhuman performance. More interestingly was the algorithm AlphaGo 0, which was an algorithm that was not shown any human information to play this game. They were just giving the rules of the game to the algorithm and allow it to play it against itself. And through reinforcement learning, it could really very quickly improve. What you can see here on the right is the performance of this algorithm. In less than 2 days of training, they could really overcome the performance of the best human players. And this machine won by 100-0 against AlphaGo. So experts in Go claim that this algorithm was able to discover, through reinforcement learning, completely new strategies to tackle this game. Of course, these are just games. These are examples and models for complex tasks that we want to really confront our algorithms with. We want to maybe look at things that can be more useful for us, such as sustainability goals, the SDGs. The SDGs, and I'm sure that many people in the audience are familiar with them. The SDG agenda is basically developed by the United Nations in 2015, and this is a shared blueprint for prosperity and a sustainable future. The SDG agenda comprises 17 goals and 169 targets. These targets are basically sub-goals, and the point of this SDG agenda is that it includes a very wide range of objectives, from ending poverty to solving the climate emergency. So it's really a very, very broad set of goals where it's actually quite difficult to have the knowledge to be able to tackle all these objectives simultaneously. So what we wanted to do was to basically assess whether there is any published evidence of artificial intelligence being used as an enabler or an inhibitor to achieve each of these goals. Okay, this is a question that we asked ourselves around 2017, maybe. That's when we started to think about this over lunch with other colleagues. And then we really realized very quickly that, first of all, there was no evidence at the time to answer this question that we had. And second, we require a very multidisciplinary team to be able to tackle these questions because of the broad range of areas that are included in the SDGs. So we assembled a quite broad multidisciplinary team. This ended up being published in Nature Communications in 2020, so 4 years ago. Some of these results have been updated later on, but many of the things that I'll be showing you today are still applicable nowadays, which means that we were not so wrong thinking forward of what things would actually lead to. And I would like to start by presenting you the team. We had a total of 10 people, 5 men, 5 women from all continents. We had experts in engineering, in applied and fundamental machine learning, experts in ethics, experts in economics, biodiversity, ecology, experts in sustainability and systems thinking, and also experts in kind of visionary AI. So in this team, we could really work in a very multidisciplinary setting so that we could make sure that we could tackle all these challenges that are included in the SDG agenda. So this was a very, very fun experience, challenging as well. And the first thing that we did in order to make our job easier was to split the 17 SDGs into 3 main categories. This is a quite standard classification by the Stockholm Resilience Center, by the United Nations. So basically, these SDGs are divided into the ones relevant to the society, the economy, and the environment. Okay, so these 3 main areas are the main focus of what we will be talking about today. And I'm going to explain a little bit our process. So what you see there is part of our supplementary material. Together with the paper, if you go to the website, and you can get the reference later on anyway, what we do is for each of the targets, remember 169, we report whether there is evidence of AI acting as an enabler, AI acting as an inhibitor of that particular target. We give a reasoning, and we give references. So a number of references supporting our claims. And in some cases, you will have AI being both an enabler and an inhibitor. In some cases, there will be no evidence. So we documented that for each of these objectives. And we perform what is called an expert elicitation process. So we had, first of all, a couple of experts. So in this case, Sami and Simone would be the experts assigned to that sustainable development goal. Then we had a couple of reviewers. So in this case, Yolanda and myself, we would be the reviewers. And our idea is to act as a red team, basically. So we had to come in and find holes in their argumentation, trying to really criticize their approach so that we could eventually discuss and converge in such an expert elicitation process, right? So we could really have a comprehensive view. And this process was carried out over more than a year, or almost 2 years actually, including workshops, focus sessions, online discussions. So we could really have a quite comprehensive overview of all these topics. And again, you can find all the details and all the examples in the supplementary material. You can just go there and download it. Today, I will highlight just the main results, the main take-home messages, but you can see a really complete description in that supplementary material over there. So, some results. First of all, the message that we find is in general positive. 79% of the targets can be positively affected by AI, whereas 35% of them can be negatively affected by AI. Of course, this means that although the message is positive, we should not neglect the cascading effects leading to one single target being negatively affected can have consequences in all of them, right? So we should not neglect those negatives that we can see over there. The environment is, in principle, the area with the highest positive potential, and in principle, the society could be perceived as the area with the highest negative potential of AI, as we have maybe observed in the years after this article was published. No? So this is something to be aware of, and once again, to still focus on interpretability aspects, which are quite essential for this type of methods. If we go a bit into more details, what I'm showing you here on the left is the positive impacts. So for each of the SDGs, what I'm showing you is the percentage of targets being positively affected by AI. On the right, I'm showing you the negatives, again, for each of the SDGs. You can see two numbers. The number in brackets will come later. I will tell you more about it. The number without brackets corresponds to the thin color line, so this line over here. And the point is the following. The thin color line is basically representing if we find at least one reference documenting a positive or a negative impact. Okay, so that's what we are showing here. You can see that the green color is larger than the orange color. The positive effects are in general more prominent than the negative effects, but of course the negative ones are not negligible. Now, what happens with the darker colors inside and the numbers between brackets? What happens there? Well, those ones were obtained by taking into account the strength of the evidence. So what we did was to look at all the references that we have in our supplementary material. We have at least 4 or 5 references per target, and we have 169 targets, so there's quite a lot of references there. All of them were divided into 4 categories, A, B, C, and D. A type of references are the ones where we see the most robust evidence and the easiest to generalize evidence. So we consider a weighting factor of 1. And then we go down in this hierarchy until the D type of references, which are the weakest, the most speculative, and the most, basically the hardest to actually implement in a real life project. And those are D type of reference with a weighting factor of 0.25. Basically, any evidence based on a D type of reference would count only as 25% of the target being affected, positively or negatively. So taking into account this strength of the evidence, what we did now was to look again at the figures and plot the values in brackets and the darker color. So the darker color that you can see is taking into account the strength of the evidence, and obviously by definition the dark area is going to be smaller or equal than the light area. And here we can actually see something quite interesting. By analyzing the reduction between the light and the dark color, we can actually assess areas of, if you wish, of research gaps, right? Because the evidence is not that strong. And if you look at these figures on the negatives, the negative effect of AI on the environment and on the society experience a very large reduction when I take into account the strength of the evidence. Okay, of course there is evidence, but there's a research gap. And interestingly, in the positives, if you look at this region over here, this big reduction, the positive effects of AI on the economy are another research gap. So again, there is evidence, there are studies, but the actual implementation in real cases and its future evolution, that's not so clear. No? I mean, everybody claims that automation will bring in new jobs, but the evidence is not there yet, right? So basically, what we've used this figure for is to justify what should be important research gaps and areas that should be emphasized further in the future when doing AI research. Okay, so this is about the overall results. I will now mention some highlights, some examples. Remember that all the details can be found in the supplementary material. So if you want to really go deeper, you can just access that data set. But generally, the positive impacts of AI have to do with new technology being enabled. So we can do something that could not be done before. One example is a quite clean example on SDG 1, on no poverty, where AI allows us to analyze satellite images to track regions of poverty. And that's very crucial information that can be helpful to be able to really have better actions to tackle poverty. The negative effects in general have to do with uneven access to AI resources and increase inequalities. I mean, that's basically, there's many examples, but if you generalize a little bit, that's the main message. You increase the access inequality and the social redistribution of resources gets unbalanced, essentially. That exacerbates the negative effects on SDG 10 on reducing inequalities. So clearly that's a big challenge that we have all experiencing more and more in the past years. So these are the two general examples. If we go a bit more into some important questions, a year after this paper was published, we had a workshop at KTH, similar to this one, where we discussed future steps, and future actions to take. And we were happy to have, for example, Max Tegmark and many other high-profile people really discussing these issues. And one of the topics that we really highlighted was in the context of SDG 5 on gender equality. There's two important questions related to gender equality. One is the gender data gap. Of course, a lot of the data that is being used to train these models is steered towards men, and that's bringing inequalities in the outcome of these models. And the second is the inequality in the workforce. So unfortunately, there is a big disparity between, if you look at the workforce of the people developing these models, both in the context of the racial variety and of course of the gender equality, there's some important issues there as well. And these people that are developing the AI models are also making crucial decisions about how these models are being implemented and deployed. So that's why these two gaps need to be addressed in order to have a proper deployment of these models in our society. So SDG 5 and some additional examples that I would like to highlight. If we think here of SDG 7 on clean energy or SDG 13 on climate action, what we see is that almost all the targets are positively affected by AI. So clearly there's a wide range of applications where we can employ these systems. For example, we can have a better assessment of the supply and demand of energy, and we can prioritize cleaner sources. I mean, this is something that AI is very good at. One aspect that I would like to highlight also is the energetic cost of these systems, right? So when we wrote this paper, around 1% of the total electricity worldwide was used for information and communication technologies, and it's expected that by 2030 this will reach 20%. I'm pretty sure that with the information that we have now, this number is much higher, if you think of the very large LLMs being trained by OpenAI and company. So this is a problem, because if you're trying to use AI for the environment, but the environmental impact of AI is not taken into account, that's something that we are not doing very well. And here there's several things that we should keep in mind. And one of them is being aware of the cost of these systems when you train them. I do a lot of computations and computational fluid dynamics. That's one of my main areas. And every time you use a large high-performance computing center, you get a quite important number in addition to the economical cost of your simulations, and that's the environmental cost in terms of CO2 emissions. So those numbers should be in your mind when you're using data and AI systems to really train these models. And the second one is most of the times we know something about the system that we're trying to model. I mean, if we are engineers, we may know some physical properties about the problem that we want to solve. So we should embed those physical properties or whatever information we have about the system in our model. I mean, that's something that not only will help to reduce the training cost, but also will increase the accuracy of these models that we are developing. So basically, physics-guided machine learning should be a must. Now we should really put everything that we know in the model, essentially. Okay, so this is about environmental cost, another important challenge. And now there's certain areas that interest us as a technical university, right? I mean, SDG 9 on innovation and industry. Clearly, there's new opportunities by AI. We can optimize electricity usage. We can have smarter models and smarter cities. We can split complex tasks into simpler ones to optimize processes. But of course, once again, I would like to bring up the uneven opportunities to access AI. This could lead to a loss of jobs because we require higher qualification. We can exacerbate the existing inequalities and displacement of tasks from developing countries to other contexts that could really increase their challenges. So there's some issues to keep in mind in the context of innovation and industry, and this also applies to education. That's the other topic that is relevant to our university. Clearly, there's new opportunities like intelligent tutoring, being able to have better resources for remote teaching, personalized student follow-up, increased access to education. I mean, we can really see even with YouTube, the capabilities that we have now to share lectures and to share material and how that can be tuned by the needs of the user. But of course, the biases associated with AI systems are also a challenge in the context of education. So if we are thinking of local differences in the culture and the needs of the students, issues with data protection, and also the need of highly qualified professionals to be able to exploit these systems, then we see a picture that can be a bit scary also in the context of education. So once again, lots of potential, lots of great opportunities. We should be aware of the risks and we should put the means to minimize those risks. A couple of things that I like also, a couple of additional risks have to do with, I like it because this slide, we wrote it in 2020. And the years after have kind of confirmed a little bit what we were saying at the time. First of all, is a political polarization, right? I mean, we are witnessing biased results of elections, biased results of social messages, the pandemic, the war. I mean, all these important large-scale events get exacerbated by the use of algorithms in social media that create echo chambers, right? In fact, it's actually funny because most of the message has been that in social media, you only hear what you want to hear, and therefore that reinforces your own ideas. But research has shown that it is true that we're more polarized than ever, but it's not because of those echo chambers, it's because we're exposed to more ideas than ever. And that's what's actually leading to even stronger ideas and even more polarization. So that's maybe something to keep in mind also in the context of the algorithms that are being deployed behind social media. Another important conclusion is regulatory oversight, which should be prioritized over regulatory, should be kept in mind because regulatory insight is essential, right? So if we involve only politicians in development of regulations of this technology, we might end up with a situation that regulation is not relevant or even enforceable if we look at the actual applications, and therefore it's very important to involve experts in the processes of regulating these systems. So regulatory insight is actually essential in this context as well. And this has implications to SDG 16 in the context of strong institutions. This is something that we did in 2020, so during the pandemic. This has to do with contact tracing apps that were proposed at the time. So this, in principle, were a good idea, with important implications on SDG 3 on health and SDG 10 on inequalities. The problem is that their strategy of communication of the governments was not so good, and we could see that their effect was limited on the pandemic. At the time, what we wrote is that it's essential to develop contact tracing apps that prioritize decentralized data gathering, So, for example, the UK app at the beginning was really centralized. That was a big issue. And what we did was to analyze several apps, the one by Austria, Stop Corona, the one by the UK, Trace Together in Singapore, and the last figure over there is the European Data Protection Board guidelines, so basically the European guidelines. And we ranked these apps and these guidelines in terms of the impact on the citizens, the technology, and the governance. So we could see that Stop Corona was actually pretty good. We were more strict than the European regulations. The biggest issue was the communication. In the governance section, what you can see is that many of these apps were deployed in a way that was intrusive in the citizens, and in fact, the governments were not able to properly convey the importance of these apps in terms of data gathering and individual safety. And we ended up with people being scared of these apps, while at the same time they were downloading TikTok, which is a million times worse in terms of data protection. So this is a lesson I think that we should learn for the future, and it's the fact that one should bring in the technology together with a proper communication strategy from the governments to ensure the trust on these systems. I'll talk a bit more about this point of trust, but I would also like to discuss these interactions that you can see here. In this figure, we are looking at interactions between the technology, the individuals, and the governments, and the thickness of the arrow is the speed of change. So clearly the technology is going quite fast, imposing new needs on the individuals and even stronger needs on the governments in terms of legislation, standards, and regulation. And the governments are acting really, really slowly compared with the needs of the changes that we are experiencing. And everything happens with the environment as an underlying layer, where we should also be concerned with our positive and negative impacts and the resources that we use. So this dynamics is also something to keep in mind. And talking about the trust of the citizens, this is something that we wrote a year after. This is in Nature Machine Intelligence. We talked about interpretability because many of these deep learning methods are not interpretable. They're black boxes, so you don't know how the input is related to the output. But if you want to ensure that these methods will be helping to achieve these goals, you need to make sure that there is accountability and transparency. So you need to ensure that you can have interpretable methods. What is interpretability? Interpretability, because there is a bit of confusion in the literature between different terms, explainability, interpretability. In this context, we define interpretability as being able to have a clear model that connects the input and the output, for example, an equation. And that's what we claim in this paper. If you're using AI for the objective of reducing poverty from looking at images from satellites, the example that I gave before, typically you have the satellite images, you apply some computer vision tools, some CNN, for example, so we end up with filter activation maps, and then different factors from these images are going to be used to make the prediction of the consumption per capita and per day. So basically this P, which gives you the threshold below or above poverty line, basically. Now, there's different factors, like let's say the intensity of light in the evening, the distance to a bigger city, the amount of roads in the pictures, and a neural network will give you a value of P without knowing how these input parameters are connected. Through interpretable deep learning, and here there are aspects like symbolic regression and inductive biases that help me to end up with equations mimicking the prediction capabilities of these neural networks, then we may end up with equations where we can see the relative impacts of all these parameters. And these equations, these interpretable models are essential to be able to see the dynamics over time of these predictions and to be able to coordinate better actions. Now, this is an example of SDG 1, but the classical example is on medical applications. Sometimes easier models are preferred because they're interpretable, even if their accuracy is much lower than deep learning models. So we should really embed the interpretability layer on all these deep learning configurations that we have, basically. Okay. What are we doing now? So this was some years ago. In the meantime, we have been working a bit more on extending these results. What we are doing now, using LLMs, so basically large language models and natural language processing, is to analyze large amounts of documents, very large amounts of documents, research papers, policy, national indicators of sustainability, to find synergies and trade-offs among the SDGs, among the sustainability agenda. And with this information in mind, what we want to do is create a matrix of positive and negative effects between all the goals, between all the sustainability goals, and perform optimization at the end. So if I want to, because of course, many of these goals are conflicting, right? I'm not going to be able to achieve them simultaneously. So if I want to get the maximum return on SDG 13 on climate action, how should I do it? And with this objective way to find hidden connections among the SDGs and develop optimization strategies, I can be in a very good position to be able to make these decisions from a policy point of view. And this is research funded by Digital Futures, actually. We have my collaborators, Francesca La Rosa and Francesco Fusonerini, who are really working on this with me and with other people. So this is really something that I believe is essential to redefine the future of sustainability agendas for the UN. We're very excited about this. A couple of additional topics, talking last year about this this moratorium, this open letter by the Future of Life Institute, on stopping the large AI experiments. Yeah, we really were against that at the time. So we wrote a couple of perspective papers, one in Nature Climate Change with Francesca La Rosa, and another one on the frontiers of computing science. So basically what we claim is that you cannot just stop in an arbitrary way the progress of this technology. First of all, because many of the solutions to the climate emergency are within these tools, and we can really find new ways to really tackle the challenges, but also because most of the fears that some experts are having about this technology will be overcome with this technology itself, right? So we should really be focusing on regulation and proper regulatory frameworks rather than on fear and stopping things, because progress and research is what should help us to solve challenges. That's how we have been doing it. So a couple of perspective articles there that could be helpful if you're interested in this topic. And I would like to also make some notes about architecture also, and cities. This is kind of like the main topic of today. SDG 11 or sustainable cities and SDG 13 are key SDGs where AI can really help. All the targets of SDG 11 can be positively affected and achieved through AI, in particular in the context of air pollution in cities, because pollution kills 800,000 people per year in Europe. So this is kind of like a big problem where we are actually trying to develop solutions that could help us. And my main area is in fluid mechanics. I'm an associate professor in fluid mechanics. We perform very highly detailed simulations of the flow around obstacles, basically models for buildings. And our main idea is to use these sparse measurements, which you can put in the street, to, with computer vision tools, reconstruct the flow in 3D, reconstruct the temperature distributions, and reconstruct the pollution levels in these environments. So we are able to create quite good models. Here on the right, you can see the level of detail that we have in our simulations. These are two buildings with different separations that lead to very different regimes of the flow between the two buildings. And we have quite good computer vision methods to reconstruct from the sparse measurements the dense representation of the flow, temperature, and pollution levels in different configurations. So we are kind of working also from a technical point of view on leveraging the capabilities of AI to improve these predictions. We actually, if you're interested, we have a review paper in Nature Computational Science where we highlight the potential of machine learning to improve simulation methods, in the context of fluid mechanics and in the context of what can be used for cities. Okay, and that's all I have for today. Thank you very much for your attention. I'd like to highlight a little bit the possibilities that we have in the context of AI and the SDGs. We're using LLMs to really redefine sustainability agendas, and we are also using quite powerful computer vision tools to apply these prediction methods to cities and to really be able to better assess the pollution levels and create better solutions for sustainability in urban environments. I'll be happy to take your questions.
Hello. Does anybody would like to have a question here in the audience?
I do have a small question regarding the graphs where you were showing in the overall impact of the different SDGs. I did notice that we can see so very high comparison on the positive ones over the negative ones. And could that also be affected by some bias of publication in regards to favoring always positive results over negative ones? And if so, how was that accounted for?
Yeah, that's a good point. Indeed, there is a bias towards positive results. We really try to be quite critical in the expert elicitation process, because many of the effects, especially the negative effects, but also many of the positive, are not obvious in the papers. So if we are analyzing, for example, a study that is trying to reduce the hunger, the SDG 2, reduce hunger, so it may be able to more efficiently exploit water resources, and there's some very nice results and very nice applications of projects for water resources. The clear implication is a positive impact on SDG 2, but the not so obvious connection, which is the role of the reviewers, is to realize, look, if you're using this type of methods without the proper boundary conditions and without the proper implementation, you're going to have negative impacts on the SDGs related to life below water, and probably also life over water, life on land. So many of the negatives came from the discussions and the expert elicitation process. So even if there is a bias towards positive results, we try to bring in the negative ones as well, which are implicit in those positive results. Now, having said that, the capabilities that we're exploiting now with LLMs and NLP really help us to find hidden connections, and many of them are also negative and not explicitly stated in the work, in the articles.
I have another question. Thank you for the talk.
Thank you.
So regarding the environmental impact, how and the negative effects of training LLMs and so on, is this thought of as over time as well? Because I mean, I'm just an architect, but the way I've understood AI progressing over time is that the algorithms are optimized, and so you can run, more compute with less power. Is this something which?
Yeah, that's a good point. I mean, so far the trend that we have been observing is on making very dumb models train on very large amounts of data. And if you think of OpenAI and many other companies, they have hundreds of thousands of GPUs literally, and they just throw in more data. And unfortunately, it's giving better results. I mean, at some point, all these LLMs, pseudo-emergent properties come from just the sheer amount of data. Luckily, what I'm also observing is that it's actually quite rather limited what you can do with only text and with only the self-attention mechanisms of transformers nowadays. We need something smarter. It's not just about building larger models and having more GPUs and burning more compute power than anyone, because that has a limit. And we are already experiencing that limit. I mean, LLMs are powerful and they give the appearance of intelligence, if you wish, but they're not intelligent, right? They're very, very simple models at the end of the day. Conceptually, they use a lot of data, and therefore they can get extremely impressive performance, but the model itself is actually simple. So I hope that it's going to go in the direction of developing smarter models in a research context, and not just companies burning more GPUs. And I believe people are starting to realize that we need to be a bit smarter in the future development of AI systems.
I would also like to ask you, thank you for your presentation. It has been really interesting, and
Thank you.
I have been really taken by many parts. How do you think that AI can help achieve more gender equality when, for example, when using AI generative models, usually we see images of women that follow same standard, but I guess there are many other ways. How do you think this can have a positive?
Yeah, no, that's an excellent point. I think the answer is not in AI itself, but behind the AI. I mean, these 2 points, right? The data and the workforce. Those are the 2 gaps that need to be addressed. So, I mean, we need to make sure that systems are trained with a wider representation of the genders in the data that is being used, in the architectures, in the choice of the type of system and the type of prediction that is being made, and also in the workforce. So really, you need to have a much broader representation of the people developing these algorithms in order to be able to ensure that these important questions are being addressed. So I don't think it's a question, I mean, of the AI technology itself. Of course, you need to be able to put the necessary limitations and the necessary safeguards in the systems, but it comes with the data and the people who are creating those systems.
Ah, that's so interesting. Thank you. And what would you say to people that claim that AI pollutes a lot? It requires so much computer power and has these disadvantages.
Yeah, no, those are very fair points. And first of all, if we want to use AI for sustainability, we need to be aware of the sustainability of AI itself. That's clear. And I think, the two of the points that I mentioned that are essential are to really be aware of the cost and to really embed the knowledge that we have on the system that we're trying to represent. More importantly, we need a change of paradigm, right? The thinking, as we were also discussing with your question, has been to create larger models. We need to create smarter models. We need to just be better at creating these systems. So yeah, the way to limit the environmental impact is to really do our job better and try to make sure that we are creating attention mechanisms, that we're creating predictive frameworks that better exploit the data that is given to them. It shouldn't be about size of the data set. It should be about how we're using it.
So thank you so very much, Ricardo, for presenting very, very interesting research and promising too for a better future with AI.
Thank you. We hope so.
Really inspiring. Thank you very much.